Good afternoon. So we are ready for today's class. So from all the feedback that I received, I have tried to keep the whiteboard as straight as I could, and I hope this will make things easier for you all to see and then comprehend. Okay. So as you all can see, that today the topic of our class is Maxwell's equations. Okay, and while we are discussing the Maxwell's equation, what we are essentially going to do, we are actually going to follow exactly what our syllabus wants us as per the Maxwell's syllabus. We will be writing down or discussing the Maxwell's equations in terms in their integral forms, and then we will be changing these integral forms into the differential forms. And while we are writing down or we are changing from integral to differential form, we will also be discussing that what is the physical significance of each of these four Maxwell equations. And essentially, if you see here, I have written as a fourth point the modified Ampere's law and something called the displacement current. The last point that you can see over here, which I have also marked with a star, is basically the fourth Maxwell's equation, and it brings in the concept of a very new thing, which is called the displacement current. And while we are bringing in the displacement current, we essentially modify the earlier law, Ampere's circular law. And while doing this was actually done by Maxwell, and that is why finally modified Ampere's law comes in as our fourth Maxwell law. So these are the things that we are going to cover in today's class. Okay. So before we actually start our class and we directly go and write and discuss about Maxwell's equations, there are 3 to 4 points which can be considered as the prerequisites. Prerequisites means a few information which I know all of you are aware of, which you all know. However, let me just remind them so that when we are using them in today's class, it will be much easier for you all to understand and comprehend. So we will first begin with the 4 prerequisites that we are going to require in today's class. So what is the first thing which I would like to remind all of you about? The first thing which I would like to remind you actually is from our vector, from the vector chapter. And what is that? And suppose if there is a vector, say vector A, then flux of that vector, flux of any vector, say A. How will I write the flux of any vector A? I will write it as say the vector A dot ds over a surface. Okay, so whenever we are trying to find out the flux of a vector, what essentially I want to do? Flux of a vector across any given surface, then I will take the surface, say the surface is S, I will break it into very small little surfaces called ds's, and then we will find out the dot product of the particular vector with the small amount of surface area, and then when we are integrating the entire surface, we will be getting the total flux of the vector. So whenever we are coming across the flux of any given vector across a surface, remember which integral are we working with? We are working with the surface integral. Alright? So this was the first point which I wanted to remind all of you. Now, the second point, which is very important as well, is something called the EMF flowing in the circuit. The EMF in the circuit. Now see, we are going back to our electricity classes. When I say EMF, what do I know? That if there is an EMF, the electromotive force in a circuit, there is as if a presence of current, right? And obviously there will be some voltage as well. Now this EMF can also be written as the line integral. This time we will be writing it as the line integral over a closed contour. Let me first write it down and then I will explain this to you. See, EMF within a circuit. When I say circuit, obviously that circuit has to be a closed one, and that is why I am using the notation of a closed circuit, a closed loop. So within this closed loop, if there is the flow of current, then who is causing this? The EMF is causing this, and the EMF is exactly equal to the line integral of the electric field vector over the contour that we are considering, over the circuit that we are considering. So please remember, whenever we are talking about the EMF in a circuit, it is nothing but the dot product of the electric field vector taken over a small contour part, and then we are integrating it over the entire circuit. And please do not forget that this is a closed circuit. Obviously, without the completion of the circuit, without closing the circuit, we do not actually have any meaning of a current flow. Right? So this was our point number 2. That point number 3 and 4 are actually 2 laws. And those laws are essentially from, again, vector integration. And what are they? The first one I would like to remind you is called the Gauss Divergence Theorem, which I am writing as the GDT. And also, I would like to talk about the Stokes Theorem. Alright, these are the 2 theorems which I want you all to just brush up your knowledge about. And what is that? Now, before I just write down the mathematical functions, let me just remind you that when we are doing the integration of vectors, there are basically 3 types of integrations that we generally come across. One is the line integral, the second is the surface integral, and the fourth, which exactly is not a vector integration, yet we come across a volume integral. Right? The microphone is not working properly. Are you able to hear? Something or the other will always create some problem. So is it okay now? Is it audible? Hello? Microphone is catching something else? Is it better now? Okay. So I hope we can make do with whatever is the situation at this moment. Maybe it is catching up some other noises from outside. Okay. So let's resume our class. So what I was telling you, that we come across a line integral, we come across a surface integral, and we also come across the volume integral. And depending on our requirements, these 2 theorems help us to convert a line integral into a surface one, or a surface one to a volume. Alright, so we will be requiring both of these while we are actually working with our Maxwell's equations. Right? So let us see how the mathematical combination of the Gauss divergence theorem as well as Stokes theorem looks like. Alright, so when we are going to write the Gauss divergence theorem, remember there has to be some kind of a divergence of some capital coming in. Suppose I have a vector, say A, then as per the Gauss divergence law, what can I write? I can write that the surface integral over a closed surface. Now the surface that I am writing is a closed surface. The closed surface integral of any vector, say vector A, is equal to divergence of the same vector over the volume V. Okay, so please carefully note one point all of you, that this surface that we have written here as well as this volume that we have written here are not independent of each other. It is not that this S is an arbitrary surface and this volume is any given volume. This volume V is actually the volume which has been suspended within this closed surface. Okay, so when I am trying to find out the closed surface integration, this surface integral A dot ds, obviously you will now agree that this is the flux over this closed surface S, that will be equal to the divergence of this vector taken over the same volume V. This volume V has been enclosed by this surface. Okay, so this is what we come to know from the Gauss divergence theorem. Fine. Now let me tell you about the Stokes law. This is our point number 3, which I would like to remind you as our prerequisites. Now, as the last prerequisite point, I would like to tell you, as we were discussing, about the Stokes theorem. Now, what does the Stokes theorem say? Now, Stokes theorem, once again, essentially joins two types of integrations. And what is that? It says that E dot dl. Now, when I'm writing dl, remember this is a line integral over a closed contour C. Alright. Now, over a closed contour C, this will be equal to curl of E dot ds over a surface. Okay, I hope everything is visible. Now let us try to understand that. Now see, when I am talking about a closed contour, when suppose this is the contour that I am considering, this is closed. So this contour will be containing a surface S within it. And this surface is exactly the surface that has joined this C and this S in our Stokes theorem. Fine. Now what are we getting? What are we seeing here? That when I take the line integral over a closed contour, say of any vector, say E, then it will be exactly equal to the curl of that same vector taken as a surface integral over this surface which has been subtended by this closed. Alright, so these are the 4 points which we will be keeping in mind while we are discussing our main topic of Maxwell's equations. So I hope all of you have followed and all of you have refreshed your memories about all the 4 points that I just discussed now. Alright, so now let us begin our real topic of Maxwell's equation. So the first Maxwell's equation, we will actually begin with our first Maxwell's equation. So let me just bring it to the first Maxwell's equation. Now, first Maxwell's equation, when I say, is actually nothing but the Gauss's law of electrostatics. Let me just write it down. This is nothing but the Gauss's law of electrostatics. I hope you all will understand when I write this is actually electrostatics. Because of the less of space, I am just using the abbreviation. So, first Maxwell's equation is nothing but the Gauss's law of electrostatics. Now, something must be coming into your mind that what does Gauss's law of electrostatics say? Let me first write it down and then we will discuss. We write the Gauss's law of electrostatics like this. I know when I am writing this, you all are remembering the particular Gauss's theorem, Gauss's law. Now see, what have we essentially written over here? Just remember the prerequisites that we were discussing. We have discussed that when I take a vector and I take the dot product with a small surface and then I integrate it over the entire surface, what am I actually calculating? I am calculating the total flux. And since we are writing about the vector E here, which is the electric field, so essentially what have we calculated in the left hand side? We have actually calculated the total amount of electric flux. And from where is this flux coming out? This flux is coming out from the closed surface S. And how much? What is the magnitude of this electric flux coming out of this given surface S? It's nothing but 1 by epsilon 0 times the total charge contained within this closed surface. Right? So essentially this is what you can say that this is the Maxwell's equation written in the integral form. Remember I was telling you that every Maxwell's equation can be written once in integral form and then also in the differential form. Now obviously you can see over here that there is an integration. So this is the integral form. So now what we are going to do in the next step would be to convert this integral form into the differential form. These conversions are very important from the point of view of our exams because generally it is asked so. Right. Now see, what about this charge Q? This charge Q is contained within this closed surface S. Now, let me just what to say? Let me just try to make you understand this fact. Suppose I have a closed surface, a closed 3D surface, which is known as S. And inside this closed surface S, what is the amount of charge which is contained? It is the charge which is Q. Now, what we can do over here is that we can consider that this charge Q is uniformly distributed over the volume, and we can write this total charge as integration over the volume of a quantity called rho. And just think of it. What can be this rho? This rho is as if total charge is something into volume. So total charge I have written as something into volume. So what can be this rho? This rho actually is nothing but the charge density, rather the volume charge density. So as if what we are considering that this charge Q is completely spread over the entire volume V, which is contained within our surface S, as a distribution of charges with a charge density rho. Sometimes you will see that we also write it as a rho V. Rho V determining or designating that this is the volume charge density. So I can always write this Q as an integration over the entire volume of which quantity of the volume charge density. So if I take this particular value and I replace it over here, then what will my equation look like? 1 by epsilon 0 times rho V into dV. Right? So see, we are still in the integral form only because our left hand side as well as right hand side are having integrations. Now here, see, in my left hand side I have a surface integral, whereas in my right hand side I have a volume integral. We will not be able to actually compare two such integrals, one being surface and the other being volume. So here, which theorem can be used so that I can bring this surface integral to a volume integral? Will you be able to tell me? Will you be able to understand the fact that we are now ready to change this surface integral into a volume integral? And here, which theorem is going to help us? The Gauss divergence theorem. Correct? So what I can do is, to the left hand side, when I use the Gauss divergence theorem, what will I have? I will have divergence of E over the volume V equal to 1 by epsilon 0 rho V dV. I hope all of you are agreeing with me when I write this. Correct? Okay, no issues those who are joining in late. I hope you will be able to take up whatever we have discussed. You can always see the front part later. So what we have done, we have taken the surface integral into a volume integral with the help of the Gauss divergence theorem. Fine. So now see, my left hand side and right hand side are both volume integrals. And remember, these volumes that we are writing over here are the same. This volume is the same volume which has been contained within our surface, which we have earlier talked about. So now when I am comparing these two, this integrand part, whether rho V or whether divergence of E, these can be equated to each other since the integration is over the same volume V. So can I not now write as divergence of E is equal to 1 by divergence of E is equal to 1 by epsilon 0 rho V. Can I not write it like that? And when I am writing this particular equation, what have I actually done? I have converted the integral form into a differential form. And this particular equation that you are able to see here, the divergence of E is equal to 1 by epsilon 0 times rho V is nothing but the differential form of first Maxwell's equation. So, just reminding all of you, we began with this. We began with this particular equation. This equation and this equation, both of them are the first Maxwell's equation. However, the first one is the integral form and the second one is the differential form. So I hope all of you will be able to do this conversion if asked in the examination very easily. However, at this point, now we have to think about what is the meaning of this equation or this equation. What is the physical significance? What is the physics behind this mathematics? So this is where I would like to take you all to a very nice concept. What is that? Whether this equation or this equation, there is no presence of time. Do you see this? That this equation be the integral form or the differential form, there is complete absence of time. So this equation will remain true forever for whatever be the field that we have considered, and the surface that has been kept as constant, this equation will always remain so. So this equation is a steady state equation, right? So this will not be varying with time. This is one point which you can remember. The second point is, if you look into this equation, divergence of this electric field, divergence of the electric field is having a non-zero value, isn't it? It is having a value of rho v by epsilon 0. And whenever there is some charge, if there is some charge, this divergence of the electric field is a non-zero value. And what essentially does it mean? Say the charge is a positive one. What is the inference we will draw? That the divergence of this electric field is a positive divergence, which means it will act like a source. The electric lines of the electric flux that we were discussing, the lines of forces, these flux will be as if emerging out of a point where we are doing the calculation. So that will act like a source field. On the other hand, if I consider that this charge is a negative charge, what will I have? I will see that this divergence will take a negative value, and which essentially means these lines of force can be drawn as if they are going into a particular point, or that electric field will be acting like a sink field, wherein all the lines of forces, all the flux lines will be coming into a particular point. So what essentially I want all of you all to understand here, that the electric field has a non-zero divergence, and who has created this electric field? The charge has caused, and hence we can draw the inference that the presence of a single charge, be it a positive charge or a negative charge, is possible in this universe. Correct? If it is a positive charge, it will create a source field. If it is a negative charge, it will create a sink field. However, alone, a positive charge can also exist, a negative charge can also exist. So this essentially, this first Maxwell's equation, apart from showing that this is a steady state equation, it also tells us that the presence of a lone positive or a negative charge is possible. Right? And apart from that, the last point which I would like to show you, that's divergence of this, divergence of E. Remember, divergence of any vector is a scalar quantity. So divergence of E has been equated to a constant into the charge density. So from here, I can also draw the inference that charge density is a scalar quantity, isn't it? Because divergence, the left hand side is a scalar, the right hand side also has to be a scalar quantity. So the charge distribution of the charge density that we have discussed does not have anything to do with the direction within it. It is just a scalar quantity. So this is what we can talk about the first Maxwell's equation. So essentially reminding all of you, summarizing what all we have done, we have written down the integral form, then using Gauss divergence theorem, we have converted it to the differential form. And we have also seen the physical significance of this particular equation. So I hope all of you have understood this part. Please let me have some feedback. I know the audio today might be a bit disturbing, but the rest is fine. You are able to see the board, and you have understood the first Maxwell's equation. See, I am going to cover only the part which will be required for our syllabus. I am not going into much deep or derivation of all these things. So please let me have some feedback over here that you have understood. Okay. Okay. Thank you all. Thank you all. So now it is time for us that we will go forward and we will be talking about the second Maxwell's equation. talk about the second Maxwell's equation. So now we are ready to talk about the second Maxwell's equation. And when I talk about this second Maxwell's equation, it again brings us to Gauss's law. But this time, this is not in electrostatics, rather this is the Gauss's law in magnetostatics. Alright, I am mentioning magnetostatics with the short form of MS. Okay, so essentially the second Maxwell's equation is nothing but the Gauss's law in magnetostatics. And what does it state? It states that in the same manner we had found out the electric flux coming out of a closed surface. In this case, we will find out the magnetic flux. Alright, so if I have to find out the magnetic flux, what will I write? I will obviously write, since we are finding out the magnetic flux, the vector which is over consideration here will be the magnetic field induction. So this is V dot ds over a closed surface S. Now, as per the Gauss's law of magnetostatics, the magnetic flux emanating or coming out of a closed surface is exactly equal to this. This is the so-called Gauss's law of magnetostatics, or we can also say the second Maxwell's equation. However, what type of Maxwell's equation? Obviously, since there is the integration sign here, you all will agree if I tell you that this is the integral form. Okay, Yusuf, while we are doing the changing into differential form in this case, I hope you will be able to understand in the earlier case as well. So please be with me and try to understand when I convert this integral form into the differential form. Fine. So if this is our integral form of the second Maxwell's equation or the Gauss's law of magnetostatics, how can I convert it to the differential form? Once again, what will I do? I will be using the Gauss divergence theorem. Reminding all of you, what does Gauss divergence theorem tell us? It converts, or rather it helps us to relate a closed surface integral into a volume integral. Fine. Now, if I think of this left hand side, using Gauss divergence theorem, what will I be getting here? When I use the Gauss divergence theorem, I will convert this closed surface integral into the volume integral of divergence of the same vector V over the volume V, over a small volume dV, and then we are going to integrate it over the entire volume V. But reminding all of you once again that what is this volume? This volume is the same volume which has been contained within this closed surface S. So is this clear? Yusuf, please pay attention. What we are doing while we are converting the integral form to the differential form, we are trying to get rid of this integration sign. Right? So in order to get rid of this integration sign, we are using in this particular equation, we are using the Gauss divergence theorem. And this obviously, since the right hand side is 0, this also will be equal to 0. Fine. So while I have written this down, see, this left hand side is something equal to 0. Now there are two options. One option is that the dV, the volume, can be 0, or divergence of B can be 0. Now if I take the option that the volume is 0, my entire problem disappears. There is no physical significance that the entire volume is going to 0. So what we have to essentially consider is that for this equation to hold true, the only possibility is divergence of B itself is equal to 0. Isn't it? Divergence of B. I hope all of you can see clearly the dot that I am placing. Correct. So in this case, I had started with the surface integral B dot ds is equal to 0. By applying the Gauss divergence theorem and by considering that the volume cannot go to 0, I have now come to another form of the same equation stating that the divergence of B is 0. Divergence of the magnetic field is 0. And this essentially is nothing but the differential form. From the integral form, this was our integral form. And this is our differential form. So I hope this is understood by all of you. Yusuf, could you now understand? Right? So now that we have written both the forms, be the integral form or the differential form, now let us discuss that what is the physical significance of this factor, of this equation. What is the meaning of this equation? Now see, whether we were considering, if I tell you in terms of the line integral, I mean the surface integral, what is this integral meaning? The integral means that the total magnetic flux, coming out of a closed surface is equal to 0, or from the differential form I can say that the divergence of the magnetic field is equal to 0. Now what does this essentially mean? I know that if the divergence of any quantity is positive, what will I say? There will be a point from where all the points will be going out of it. The magnetic flux will be going out. And if I have a sink, what will I essentially see? That all the magnetic flux is coming in over there. So if I have a situation where within the same system I have a source point and I have a sink point, what will I see? Whatever is going out will be coming in through the sink. So if the source is giving out the flux, the sink will be attracting all the flux, and overall, what will I see? Overall, I will see that the magnetic flux will be 0. And essentially, this brings us to the conclusion that who creates this magnetic field? We all know that magnetic poles create magnetic field. And essentially, in a given system, magnetic monopoles can never exist. Remember, electric poles or electric charges, positive charge or negative charge could exist. However, a north pole alone or a south pole alone can never exist. However small piece I break the magnet, always there will be the presence of a pair. There will be a north pole and along with it there will always be a south pole. And hence, if the north pole is bringing out all my flux, the south pole will bring in all the flux. And hence, the divergence of the magnetic field in this case will always be 0. The total magnetic flux will always be 0 in a closed surface. Fine? Essentially, in one line, if I had to summarize this entire thing, I would say that magnetic monopoles do not exist. So, if I was to ask you what is the physical significance of the Maxwell's second equation, very easily you can say that the physical significance of second Maxwell's equation is that magnetic monopoles cannot exist. Magnetic monopoles do not exist. Right? So, is this clear to all of us? So, when we have talked about first equation also, there was no explicit presence of time. In this case also, see, there is no explicit presence of time, which means this is also a steady state equation, which means if I keep the system like this forever, divergence of B will be always 0. Right? So this is not going to change with time. Divergence of the magnetic field will always be coming out as a 0 quantity. Right? So both first Maxwell's equation and second Maxwell's equation are steady state equations. They do not vary with time. And we have seen that the divergence of electric field is a non-zero value, meaning that electric monopoles, electric charges can assume that a positive charge and a negative charge can exist. However, magnetic monopoles, a single south pole or a single north pole can never exist. Fine. So if this is understood by all of you, the first and the second equations, now let us go ahead with our third equation. Okay. So now we are ready to study our third Maxwell's equation. Okay. Now, before I actually go into this, let me just remind you about a very small point. And what is that? When we see these Maxwell's equation, see, we are writing in terms of E and B. E means the electric field, B means the magnetic field, right? So this essentially brings in the concept of the electromagnetic fields, right? Remember, light is an example of electromagnetic wave. See, a gamma ray is also. Maxwell's equations essentially are followed or is true for all the electromagnetic. There is some issue. I guess I'm no more. Is it okay now? The internet was not connected. It was showing that I wasn't connected. So I think we all are online now. Can you all hear me now? So as I was telling you, Maxwell's equations are true for all electromagnetic waves. Just keep this at the back of your mind. Right? Now let us go into our third Maxwell's equation. Now, as I was telling you that the first Maxwell's equation is nothing but the Gauss's law of electrostatics. The second one was the Gauss's law of magnetostatics. In the same line, third Maxwell's equation is actually the Faraday's law. The Faraday's law of electromagnetic induction. Alright, so see, this law, the third Maxwell's equation, is bringing us to the concept of electromagnetic induction. This was basically given to us by Michael Faraday when he did the experiment, and from there this result was then finally categorized as the third Maxwell's equation. Now let me just tell you. You might be wondering that induction. You want to remember what is induction? Let me give you a very small example. I mean, like the explanation of this particular law. Then we will be going into the equation. So what had actually Faraday done? He was doing an experiment that said he had a primary coil and say it was connected to a battery source. Fine. So he took a primary coil and connected it to a source. And close to it, he set up a secondary coil. And in the secondary coil, he put a galvanometer. By G, I mean a galvanometer. So when this connection was closed and a current was flowing in the primary coil, it was seen that the moment current starts to flow in the primary coil, the galvanometer in the secondary is also showing some deflection. Galvanometer shows deflection when there is presence of current. So essentially what was observed that even though there is no direct current source, there is no voltage source in the secondary, something was causing some current to flow within the secondary and the galvanometer was showing us some deflection. So what essentially was the inference which Faraday drew? He said that there must be induction coming in, which means that this primary coil, the current flowing in this primary coil must be inducing an electromotive force, must be inducing an EMF in the secondary coil. Here comes the concept of induction. Induction of some EMF within the secondary coil. And as per Faraday, how much was this induction? How much was this EMF? He said that this EMF was equal to the time rate of minus ddt of phi. Where what was this phi? This phi was the magnetic flux. This phi was the magnetic flux. Please note all of it. We are going to obviously discuss it, but please see here what I have written. As per the Faraday's law of electromagnetic induction, what are we essentially seeing? That the EMF induced within this secondary coil is equal to minus ddt of, or the time rate of change of, ddt is nothing but the time rate, is minus time rate of the change of the magnetic flux in the circuit. From where am I getting this magnetic flux, or from where am I getting the magnetic field? Remember, whenever there is an electric current, that can produce a magnetic field. Remember the magnetic effect of current, right? So what has essentially happened? This primary coil has induced an EMF inside the secondary coil, and this induced EMF is exactly equal to the negative time rate of the magnetic flux. So if this is understood, let us now put in the various values. Values? Why am I calling you? Why am I asking you to put in the values? Because what I have written here is the name phi b or the magnetic flux. If I ask you what will be the value of magnetic flux? Obviously now remember the first point that we were discussing as a prerequisite. When I have to calculate the flux of a particular vector, I will take that vector and I will calculate its surface integral, right? So what will I write this phi b as? This magnetic flux, I hope you all will agree that it is the surface integral of E dot ds, right? And where is the surface coming from? The surface is coming from this circuit has taken a surface over it. It has subtended a particular surface. That surface is this surface. And reminding all of you about the second prerequisite point. What is the EMF flowing in this circuit? This EMF flowing in the circuit is nothing but the line integral, the closed line integral over this circuit C of E dot dl. Am I right? So we are just writing the various values in our Faraday's law. So EMF we have replaced it by the line integral over the closed circuit E dot dl, and magnetic flux has been written as its surface integral over the same surface that this circuit is subtending. Correct. Now see, when I am doing, look into the right hand side, I have a time rate of change. Now, among the quantities in the right hand side, I have the magnetic field and I have the surface. Now, this surface is not going to change with time. I hope all of you will agree with me that this surface is going to remain constant. Whereas, the time rate of change, if there is something which is changing, it is nothing but it can only be the magnetic field. So, what I can do is I can take this ddt to the as an essential part of the rate of change of magnetic field only. Right? So look into my left hand side. In the left hand side now I have a line integral. In the right hand side I have a surface integral. And this surface integral, reminding all of you, this S and this C are not independent of each other. This surface is the same surface which is closed within the circuit C. Fine. Now, in this scenario, how can we compare the left hand side and right hand side? This is a line integral and this is a surface integral. So, we are going to use one of those theories or those theorems that we earlier discussed. And this time, it is not going to be the Gauss divergence theorem, because Gauss divergence theorem relates a volume integral and a surface integral. But now I need to relate a line integral. So tell me, which integral will I use? I hope all of you will not tell me the same answer, that you are going to use the Stokes theorem. Correct? Very nice. So how can I use Stokes theorem over here? Remember, Stokes theorem relates a line integral into a volume integral in the form. And I will now write this as the surface integral of curl of E over the same surface S. So E dot dl has been converted with the help of Stokes theorem into the curl of this electric field vector into ds, I mean the dot product with this. And on the right hand side I have the same surface, but this time the integrand is minus dt. So now we can compare the left hand side with the right hand side very easily. And when I do so, obviously the surface part is common. So what can I now do? I can then very nicely convert this integral form into the differential form and write curl of E is equal to minus d dt. Right? So when I was writing line integral E dot dl is equal to minus ddt of integration b dot ds, that was essentially the integral form of the the help of little bit of mathematics, with the help of the Stokes Theorem, we have now derived the differential form of the same equation. And this tells us that the curl of E is equal to minus del B del T. Fine, dB. Now sometimes you will see that instead of the complete integral dB dt, we also use the term del B del T. We also use the partial derivative in terms of time. We write it as del B del T. Now this can be considered in the manner that since magnetic field is a function of both spatial parts as well as temporal part. So sometimes when we are deeply thinking about it, instead of exactly writing ddt, we write del del T. But for your purposes, you can always write the full integral over time. So at this point of time, once we have written the integral form and we have converted that into the differential form, what will be our next job to do? Our next job will be to now try to understand the physical meaning, the physical significance of this equation, right? So what is the physical significance of this particular equation? The physical significance is point number 1. This is the first of, up to now, all the equations that we have seen did not have any time in them. For divergence of B, divergence of E, they were not having any time. But see, this equation is explicitly dependent on time. So this equation is a time dependent equation, which means this is not a steady state equation. This will vary with time. This is one of the first physical meaning. And the second, this is a very interesting point, which is time varying magnetic field. Whenever there is a variation of magnetic field with respect to time variable magnetic field is creating what? Is creating an electric field. Right? So as if this electric field and magnetic field are intertwined with each other. When I change the spatial parameters of E, when I take a curl of E, I create a magnetic field. But when this magnetic field changes with time, when I change its time parameter, I create an electric field. So as if a time varying magnetic field creates an electric field and a spatially varying electric field creates a magnetic field. Right? So this is the physical significance of Maxwell's third equation, or as we were calling it as the Faraday's law of electromagnetic induction. Fine. So see, up to now we have learned about 3 equations. One was divergence of E, second was divergence of B. The third relates the curl of E. Alright, so this is small little things can be kept in the mind so that you remember the order. Divergence of E, first equation. Divergence of B, second equation. Curl of B, third equation. Like this. Alright, so if we have understood this part, we are now ready to go into our final equation, final Maxwell's equation, and we are about to completely know about all the Maxwell's equations. Fine. So now let us jump into our fourth Maxwell's equation. Fine. The fourth Maxwell's equation, when I was beginning the class, I was telling you that the fourth Maxwell's equation is actually the modified, we call it as the modified Ampere's law. Modified Ampere's law. Now, you might be wondering that the earlier were Gauss's law of electrostatics, Gauss's law of magnetostatics, Faraday's law of electromagnetic induction. However, this fourth Maxwell's equation has not been stated as the law, the Ampere's law. It has been stated as the modified Ampere's law. So, what is this modification and why is there a requirement of a modification of the Ampere's law? And when we are talking about the modification of Ampere's law, obviously the first thing which we will have to remember is what is the so-called Ampere's law, right? So what essentially we are now going to do, we will first begin with the Ampere's law. We will see that there is some problem with it, then we will modify it and hence come to our fourth Maxwell's equation. Fine. So let us see is the Maxwell's law, what is the Ampere's law first. So as for Ampere, this Ampere's law is nothing but the Ampere's circuitry law. Alright, so what do I essentially have? Suppose there is a current carrying conductor. There is a current carrying conductor. Now essentially when we generally talk about current, it is generally thought that current is generally current flows in a conductor only, right? And suppose there is a current I. The current flowing in the circuit is I. Then as per the Ampere's law, if I draw a closed loop, so this is my wire and I am drawing a loop enclosing this charge, this conductor, then at any point on this I can calculate the magnetic field. And how can I write this magnetic field as? I can write that B dot ds, the flux of this magnetic field over the surface S is equal to mu 0. Alright, this was the so-called Ampere's circuitous law. So this law was given to us by Ampere. Now essentially, see, I would like to remind you of say 3 things over here. 3 small little points over here. Why we have considered or why we have written down the Ampere's law? What are the essential points that we have discussed? We have discussed that if there is current, this current can produce a magnetic field, right? So we are talking about the effect of current in the form of creating a magnet. Point number 1. Now what is the point number 2? That what consists of this current? Who made this current? We essentially consider that this current which is flowing in the circuit is caused because of the flow of charges within this conductor, which means charges have flown inside this conductor and have caused the current to flow, or the production of current has happened, right? So current is producing magnetic field and moving charges are producing current, right? So let me just write it down. Moving charges produce current. Isn't it? So we have essentially considered this. In the back of our minds, we are obviously thinking along this line. So here comes the first problem. Up to this, everything was fine. But around 1888, the AC, the alternating current, was discovered, right? So alternating current, as all of you know, that it is not a steady state current. It doesn't remain constant. It varies with time. If the particular source is 50 hertz, it could be changing its direction 50 times in a second. The AC. So what happens when we consider a particular circuit with AC and I introduce a capacitor in it? Alright, this experiment was essentially done by Ørsted. So let me just, in very short, show that experiment to you. So what was the experiment? In the experiment, we have say a circuit with a capacitor in it, and it is connected to an AC source. Fine. This capacitor is a parallel plate capacitor, and for the particular experiment that was done, there was no dielectric medium as such inserted into it. That was only air. That means there was no medium inside it. Essentially, the two plates of the capacitor did not have anything filled inside. Fine. So what was seen? At the moment the source is switched on, current will start to flow. So say a current I is flowing in this circuit. Now, what at that time the scientist did, he put a magnetic needle over here. You all know about magnetic needles? So they are basically like the sensors of magnetic field. So since there is the passage of current in this conductor over here, current is flowing. So as a result, it will be producing a magnetic field around it. Remember the loop that we were drawing? So if I am placing a magnetic needle at this point, it was seen that it is deflecting. It is not remaining unperturbed. It is deflecting to some value, which means that at this point, there is the presence of magnetic field. So sometime here, I can indeed draw a loop and find out the magnetic field using the Ampere's circuital law, right? And remember what we have seen, that this current has indeed produced some deflection in the magnetic needle, meaning that magnetic field has been created by this moving current, by this current. Up to here, no issues, no problem. But now think, what will happen at this inside the capacitor? The capacitor does not have any conduction. There are no conductors between the two plates of the capacitor, which means at this point the circuit is getting broken, isn't it? The circuit is no longer a closed circuit, right? Then what was seen when another magnetic needle was placed in this place, within the capacitor? Strangely, it was seen that this capacitor also showed some deflection. Try to understand what I just said. Not only along the point wherever there is a wire, the magnetic needle is deflecting. The magnetic needle was also deflecting inside somewhere within the capacitor, which means even though there was no flow of charge, magnetic field was still created. And this baffled the scientists at that time. And this particular law seems to be incomplete. That this is only valid in a closed loop, isn't it? This is only valid within the closed loop. But here, there is no closed loop. Then how can there be a magnetic field? Who is creating the magnetic field? Or from where am I getting any current whatsoever which is creating this magnetic field? And that is why a modification in the Ampere's law was required. Fine. It was this particular observation that even inside a place where there was no conductors, where there were no moving charges, the effect of electric current was seen. Magnetic field was felt over there also. Okay. We cannot understand. Okay. So if this is so, then how did we come across this? We actually came across this. Acha. Oh, acha. Now I understand what you are writing. Yes. This is the NTL. This is the closed contour. Please, yeah. You're right, Krishnendu. This is not the surface integral. This is the line integral. Fine. Now, from where did we get the answer of this particular question? This is where actually Maxwell gave us the answer. Maxwell actually brought in a new concept and he modified this Ampere's circuital law and finally completed the entire circuital law into a complete foolproof equation. And that is why we call it as the Ampere's modified circuital law, modified Ampere's circuital law. But how did we do this modification? What was the new concept that was introduced? Now let us try to understand that. Now, what did Maxwell say? He said that first and foremost, the concept that current is only produced by moving charges seems to be not exactly true. It is not that current is only produced by some moving charge. There is a possibility that current may still be produced by some other method, by some other phenomenon. And what did he say? Now see carefully. He said that suppose this is my circuit, right? This is my capacitor. What essentially is happening in this capacitor? When I am switching on this AC source, some electric field initially say all this plate will be turning to positive and this plate will be turning to negative. That means the capacitor would be charged. Fine. Now when this if at one fraction of moment this plate is positive and this plate is negative, can I not consider or can I not say that an electric field will be produced within the capacitor plates? An electric field will be produced and we will draw the direction from positive to negative, which means this AC has produced, this voltage has produced an electric field inside the capacitor. Fine. So there is an electric field coming into action. But now, this is not a DC, this is an AC, an alternating current, which means every 1/50th of second or maybe as many hertz we have, this is going to flip its direction, positive, negative. And as a result, this electric field that is being created is also not remaining constant. It is continuously changing itself with time. Isn't it? So this time change of electric field must be creating a magnetic field. Must be creating a magnetic field, and that must be the cause of the deflection of the magnetic medium. So essentially he said that no, it was not the current. This current was over here. There was real presence of conduction current. There was flow of charges. However, within the plates of the capacitor also, even though there was no conduction of charges, still there was a current. And he called that this current will be now named as ID. He called this current as the displacement current. Okay, and I said that the normal current which we generally think of is to be called as conduction current IC. So whenever there is the presence of the wire, the presence of the conductor, the current that will be flowing will be termed as the conduction current IC. And in place where there is no conductor but there is the time varying field creating a time rate of change of E and hence creating a magnetic field, there will still be a current, but this current will be called as the displacement current IT. And from there, he modified this equation as line integral over the closed contour B dot dl is equal to mu 0 IC plus ID. Remember, once again telling you all that this IC is the conventional conduction current and this ID is the so-called displacement current. Now, why is this name displacement current? I will be coming in the next class. See, the duration of the class has already past 1 hour. So I hope I will not be extending the class anymore today. So tomorrow when we start once again, we are going to catch up from this very point. Okay, so we are going to once again start from the Maxwell's fourth equation. We are going to actually cover up this. Alright, so now before I end up the class, just let me give you a very small recap or summarization of the class. What all we have discussed? We have completed the first 3 Maxwell's equations. The first 3 Maxwell's equations which had divergence of E, divergence of B and the curl of E within them. We have converted all the 3 integral forms into their differential forms. We have also considered their physical significance. We have tried to understand the physical meaning of all the 3 Maxwell's equations. But because the time is, the class has already gone ahead by 1 hour, I would like to end up the class over here. We will begin from the fourth law, the fourth equation from 2. Alright, so that is all for now. So if there are any more doubts, we can always discuss. So thank you all. Thank you all for joining me. So hope to see you again tomorrow. Bye bye all of you.